In this video, we're going to look at how to balance an aqueous redox reaction with oxygen and hydrogen involved when it occurs in basic solution. In previous videos, you learned how to balance simple redox reactions, ones that don't contain oxygen or hydrogen, following the general steps for balancing. And those involve separating your net reaction into two half reactions, balancing the half reactions by mass and charge individually, and then adding them back together, making sure that the electrons you added to balance the charge actually canceled out when the two half reactions were added together. In a second video, we also learned how to balance oxygen and hydrogen as long as we knew that that particular reaction was occurring in acidic solution. And you used hydrogen and water, so hydrogen ions and water, to help with the balancing process. Now, if you know that your redox reaction occurs in basic solution, however, you will not have an excess of hydrogen ions to help you with that balancing process. So you will have to use hydroxide ions instead. Let's look at an example of balancing a redox equation that occurs in basic solution. Just as a reminder, you won't be able to tell just looking at your reactants and products for the equation that you're given whether it's occurring in acidic or basic solution. That information has to be provided for you. So make sure that you look for it in the setup for your homework problems as well, whether you're solving for this in acidic or basic solution. Now, whatever type of solution you're dealing with, the first steps for balancing that redox reaction are going to be the same. You're going to separate the reaction into two individual half reactions. So we're going to look at our reactants here. I have zinc and I have hypochlorite ion. They are going to be separated to become the reactants in my two half reactions. And on the product side, I'm going to separate the products that I'm given by matching them up with the reactant that they must have come from. So zinc must be transformed into the zinc hydroxide product. And hypochlorite matches up with my chloride ion product. All right, our next step is always to balance those half reactions by mass. And you should always start your balancing with atoms other than oxygen and hydrogen. In this particular example, I have both zinc and chlorine in addition to oxygen and hydrogen, but it turns out that those are both already mass balanced. I have one zinc on the left-hand side and one zinc on the right-hand side in the first half reaction, and I also have one chlorine on the left and one chlorine on the right on the second half reaction. So I can actually move straight to balancing my oxygen and my hydrogen. And since this is occurring in basic solution, we have a lot of hydroxide ion floating around in that solution, and we're going to use that to actually balance our oxygen and our hydrogen. And there's two ways of doing this depending upon the form that you find your oxygen and hydrogen in the reactant and products that you're given. So first of all, if you look at your reactant and product formulas and you recognize that one of them actually contains hydroxide as part of its formula, well, you can very simply balance that hydroxide just by adding more of it to the side that needs it. So if I know for this first half reaction that on the product side I have zinc hydroxide, which contains two OH groups, two hydroxides within it. Well, I need to balance that on the left-hand side, but I can do it very simply by just adding those two hydroxide polyatomics, the anions with the negative charge, to balance out the oxygen and hydrogen. So that's the simplest way that we can balance oxygen and hydrogen using hydroxide ions. If you see that the compound or that one of your compounds, either a reactant or a product, has hydroxide as part of the formula, you can just add OH to whichever side needs the extra hydroxides. Don't forget the charge on that hydroxide that you add, though. If, however, you see that you have just oxygen that you need to balance, like in our second half reaction, we have one oxygen on the reactant side and we have no oxygens on the product side. So we need to add an oxygen term. Now you are still going to add hydroxide to actually balance that oxygen since it contains oxygen as part of it. But you're actually going to do this a little bit differently. You are going to add 2 hydroxide ions for every 1 oxygen that you need to balance. So I have 1 oxygen on the left-hand side. I am actually going to add 2 hydroxide ions to the right-hand side to balance it out. Now, the reason I do this is because I know that when I add hydroxide, I'm actually adding hydrogen as well. And I don't have hydrogen independently on the left-hand side. I'm going to have to add a second term to actually balance that hydrogen. And I can't add hydrogen ions this time. This is not an acidic solution, and we don't have free-floating hydrogen to any large degree to actually help us balance that hydrogen. The only other compound that I have in that particular environment that contains hydrogen is H2O. And so that's what I have to add. And if I add 1 H2O, well, it contains 2 hydrogens. So I am going to take care of the extra oxygen that we added, as well as those 2 hydrogens, simply by adding H2O to the other side. So if you are just balancing oxygen, figure out how many oxygens you need, and to that side that you need to add them, add 2 hydroxides for every 1 oxygen you need to add. And then on the opposite side, add 1 water molecule for every 2 hydroxides that you had to add to mass balance that oxygen. All right, now once we've mass balanced all of our half reactions, the next steps all follow the same format that we did for the rest of the redox reactions. We're going to balance each of these half reactions with respect to charge by adjusting the number of electrons. So I'm just going to erase some of my lines here to make it a little bit easier to see our charge balance. Okay, now we're going to make sure to charge balance that we have the same charge on each side of the arrow. So we just have to add up all the charges for all of the different terms on the reactant and the product side for both of these half reactions. So for zinc, that's a neutral species. There's no charge that was written up here or here in the upper right-hand corner. So that means that this is actually a neutral atom. I added 2 hydroxides, each with a -1 charge. So that means that my total charge on the left-hand side is going to be -2. On the right-hand side, I have just the zinc hydroxide, and this is also neutral. There's no charge that's written up here in the upper right-hand corner. So this is a net charge on the product side of 0. Well, 0 is definitely more positive than our -2. So we're going to add electrons to the more positive side, and we're going to add the number of electrons we need to actually bring the charge down to what we have on the other side. So I need to bring 0 down to -2. I'm going to add 2 negative charges. That means 2 electrons, each with a negative charge. We're going to do the same process for the second half reaction. Water is a neutral molecule, so that has a charge of 0. The hypochlorite has a charge of -1 based upon that charge that's written in the upper right-hand corner. The chloride ion on the product side also has a charge of -1, and the hydroxides also have a charge of -1, but I've got 2 of them now, so that's 2 times -1. Okay, in terms of my total, this is actually a -1 total on the left-hand side, and -1 plus -2 gives you -3 for the total charge on the right-hand side. It's really the total charge that you're comparing. And you're always going to add the electrons to the more positive side. So I realize that both of my total charges here are negative, but -1 is more positive than -3. So that's the side that we're going to add more electrons to. And to bring -1 down to -3, we need to add 2 more negative charges. So that's 2 electrons. Okay. Now, once we've balanced these in terms of charge, we're also going to make sure that we've balanced the electrons between the half reactions. So that just means that we have the same number of electrons that are being lost in one reaction as are being gained in the second reaction. And I should mention here, remind you again, if you've done your mass and charge balance correctly for your half reactions, you should always have one half reaction that is considered oxidation, and one half reaction that is considered reduction. So I've gone ahead and labeled them here. This is the step or the stage where you can start labeling it once you've added in your electrons. Oxidation is always the half reaction that has electrons on the product side. Reduction is always the half reaction that has the electrons on the reactant side. And what that means is that your electrons are always going to be on opposite sides for your 2 half reactions so that when you add them together, the electrons cancel out. That's the goal. Okay, now it turns out that in this particular example, we already have the same number of electrons between my 2 half reactions. So I don't need to multiply anything through by any of these equations. I just get to move to the next step, which is to add our half reactions together, canceling the electrons and any common species. And you're going to find with these particular reactions that you may have more to cancel here than just electrons. So when I add these 2 half reactions together, my electrons, 2 electrons here and 2 electrons there, definitely cancel. But I also now have hydroxide on opposite sides of the arrow. I have my 2 hydroxides that I added here in the first half reaction that can be canceled with the 2 hydroxides that were added on the product side in the second half reaction. Because they are the same exact formula, it's just OH minus, and because it's the same number, 2 and 2, I can cancel them out completely. And that means I can just carry down to the next stage the fully balanced redox equation. And so I'll carry down my zinc plus water plus that hypochlorite ion. And it becomes, on the other side, zinc hydroxide plus chloride, and that's it. So it's always a good idea to just double check your balancing, make sure that it is still mass balanced and charge balanced. So in terms of my mass balance, I have zinc, hydrogen, chlorine, and oxygen. All right, so I'm going to do this the more traditional way and write these out. So we've got zinc, we've got chlorine, we've got hydrogen, we've got oxygen. On the left-hand side, I've got 1 zinc, and on the right-hand side, I also have 1 zinc in the zinc hydroxide formula. For the chlorine, I've got 1 chlorine in my hypochlorite ion and 1 chlorine in the chloride ion on the product side. For my hydrogen, I have 2 in water on the left-hand side, and I also have 2 in that hydroxide. And for the oxygen, I actually have 1 here and 1 here. So there's 1 in water and 1 in that hypochlorite. So 1 plus 1 equals 2. On the product side, I have those 2 hydroxide groups, and each has an oxygen, so that's a total of 2 oxygens. And that is perfectly mass balanced. So we did maintain our mass balance throughout. Now, let's check the charge balance. Oops, I erased my 2 accidentally there. Let me change that. Okay, so for our charge balance, we're just going to look at the total charges on each side. And again, we've got a 0 for our zinc. We've got 0 for neutral water. And we've just got that -1 charge on the hypochlorite, so that's -1. So that is going to give us a total charge on the left-hand side of -1 when we add all those numbers together. For the product side, we've got a 0 charge for zinc hydroxide. There's nothing written here in the upper right-hand corner. So that's a neutral, considered a neutral compound. And we've got a -1 for our chloride. So that also adds together to give us a -1 total charge. This is mass balanced and charge balanced. Let's look at one more example. I'm going to start by separating the reaction that I'm given into half reactions. So I'm going to take the 2 reactants that I'm given. This is the cyanide anion, and this is permanganate. And they are going to become the reactants in my 2 half reactions. On the product side of both of these, I'm going to take the products that I'm given and match them up. So cyanide ion corresponds to CNO, which is the cyanate anion, so CNO minus. And, oops, I forgot my charge on the permanganate. That's supposed to be a negative charge there. On the product side for permanganate, that matches up with manganese dioxide, MnO2. Okay, now I'm going to balance these half reactions by mass. I'm going to balance everything other than oxygen and hydrogen first. So I have carbon, I have nitrogen, and I have manganese as well in these half reactions. But it turns out that in this example, they're already mass balanced. I have 1 carbon on the left and 1 carbon on the right in that first half reaction. I also have 1 nitrogen and 1 nitrogen on left and right for the first half reaction. And in the second half reaction, I've got 1 manganese and 1 manganese on each side of the arrow. All right, so they're mass balanced, and we can go ahead and start balancing the oxygen that we have present there. I'm going to do that by adding hydroxide anions. Okay, so when I look at these half reactions, I don't see any compound formula that already contains OH, the polyatomic as part of the compound formula. So I'm going to move straight to that second way of adding hydroxide. I only have oxygen to balance, so I'm going to add 2 hydroxide ions to the side that needs more oxygen for every 1 oxygen that I need to add. So in that first half reaction, I have 1 oxygen on the right-hand side. I have none on the left-hand side. So I need to add oxygen to the left. Since I only have 1 oxygen that I need to add, since that's how many I have on the right-hand side, I'm going to add 2 hydroxides. And I do that because in order to balance the hydrogen, I have to add water. And water has 2 hydrogens. So for every 2 hydroxides that I add, I'm going to add 1 water molecule to the other side. And that will balance my oxygen and my hydrogen. We're going to do the same thing for the second half reaction. Here I've got 4 oxygens on the left versus 2 on the right. So I need to add 2 more oxygens to the right-hand side. I'm going to add that in the form of hydroxides, and 2 hydroxides for every 1 oxygen that I need to add. Well, since I need 2 more oxygens, I'm actually going to add 4 hydroxides. All right, I realize that's extra oxygen, but that's because I'm going to add water, 2 water molecules to the other side to account for that. So that will balance both my oxygen and my hydrogen. And once we've done that, we can move on to the next step. We need to balance each of these half reactions with respect to charge by adjusting the number of electrons. Okay, so for the total charge that I have in that first half reaction, on the left-hand side, I've got a -1 with the cyanide, and I've got 2 of those hydroxides that I added. So that's 2 times -1. If I add both of these charges together, that's going to give me a -3 total on the left. My cyanate anion has a -1 charge, and my water is neutral. So that's going to give me a total charge of -1 on the right. Now, -1 is considered more positive, even though it's a negative number. It is still more positive than -3. So that's the side that I'm going to add my electrons to. And to bring -1 down to -3, my charge on the other side, I need 2 more negative charges. So I add 2 electrons. And now that's a charge-balanced half reaction. We'll do the same process for the second half reaction. I've got a -1 charge with that permanganate. I have 2 water molecules, but both of them are neutral, so that's 2 times 0, which is still 0. We add these numbers together, and it's going to give us a total of -1. My manganese dioxide has a 0 charge. It's a neutral compound, and I also have hydroxide, which has been added in here, but I've got 4 of them, each with a -1 charge. Okay, now I add together that total charge, so 0 plus -4 for the hydroxide, that's a -4 total. Well, -1 on the left is more positive than the -4 on the right, so we're going to add our electrons to the left. And to bring -1 down to -4, you need 3 additional negative charges, so I add 3 electrons. All right, and I know that I'm on the right track with my balancing because I have the electrons are on opposite sides for my 2 half reactions. That first half reaction is my oxidation one with the electrons in the product side, and the second one is my reduction half reaction. Let me erase my individual charges here. And then we'll balance our electrons between our 2 half reactions. Okay, next, we need to have the same number of electrons between these 2 half reactions so that when we add them together, they cancel. Now, it's not a simple multiplication to raise 2 up to 3. We can't do that with a whole number. So we're going to try to come up with the least common multiple for the electrons for both of these. So we'll try to raise both of these half reactions up to 6 electrons. We'll do that by multiplying everything in that first half reaction by 3 and everything in the second half reaction by 2. Just remember you have to multiply those whole number values by everything, not just the electrons. So I'm going to rewrite these down below so that I can see those new coefficients on everything. So that becomes 3 of my cyanides plus 3 times 2 is 6 hydroxides. And now I have 3 cyanates, CNO-, and 3 waters, and 6 electrons. In my second half reaction, I have 2 times 3, so that's 6 electrons, plus 2 permanganates, plus 2 times 2 is 4 waters. And then I've got 2 manganese dioxides. And 2 times 4 is 8 hydroxides. Okay, we'll add these together and see what we can cancel out. So I know that I can cancel out my electrons because I made sure that I had the same number of each in those two half reactions. But I can also cancel out at least a portion of my hydroxides because I have those on opposite sides, and my waters. I have those on opposite sides as well. Now these don't perfectly cancel out because I don't have the exact same number on opposite sides, but I can cancel out a portion. So for my hydroxide, 6 will cancel out completely on that side. And if I cancel out 6 of the 8 that I have on the right-hand side, this becomes 2 hydroxides left. For my water, the 3 will cancel out completely. And if I cancel out 3 of those 4 in that second half reaction, we'll be left with 1 water. Now I can add everything back together. So I carry down 3 cyanides plus 2 permanganates plus 1 water. And on the product side, I have 3 cyanonates plus 2 manganese dioxides and 2 hydroxide ions. All right. Now this should be balanced, but we'll just double check by making sure it's mass and charge balanced. So we'll do the mass balance first. And I will do that underneath. So I've got carbon, nitrogen, manganese, oxygen, and hydrogen. Okay, so this is a little bit more complicated here. We've got a lot of different elements. It's going to be helpful to actually have it written out so that we can keep track of everything. So I have 3 carbons on the left in cyanide and 3 carbons on the right in the cyanate. I also have 3 nitrogens and 3 nitrogens in those formulas. For my manganese, I've got 2 on the left and I've got 2 on the right. Oxygen's a little bit more complicated because it's split, right? So on the left-hand side, I've got 2 permanganates, each with 4 oxygens. So that translates into 8 permanganates, or excuse me, 8 oxygens for those permanganates. Plus I've got 1 oxygen split into that water, so the 8 plus 1. So that actually gives me a total of 9 oxygens on the left. On the right-hand side, I've got 1 in the cyanate anion, but I have 3 of those cyanate anions, so that's actually 3 oxygens. Plus I've got 2 times 2, that's 4 in the manganese dioxide, and 2 times 1, that's 2 in the hydroxide. 3 plus 4 plus 2 equals 9. All right, last but not least, we've got our hydrogen. I have 2 on the left in that water. And on the right, I've got 2 in the hydroxide. Perfect. This is mass balanced still. Okay, now let's look at the charge balance. Okay, so let's add up the total charges on the left and the right. I have 3 times that -1 for cyanide, and I've got 2 times -1 for permanganate. And it's a 0 charge for that water. All right, so when I add those up, -3 plus -2 gives me a -5 total. On the right-hand side, I've got 3 times -1 for the cyanate, Manganese dioxide is neutral, so that's 2 times 0, which is still 0. And I have 2 of those hydroxides, so that's -1. When I add all of those together, -3 plus 0 plus -2 gives me -5. So that is still charge balanced. That means that this is a correctly balanced redox equation for a basic solution.